This one. Okay. I think other students are going to join. Yeah. So that so far the way that the things are going with you, that I think that did you get a chance to have a look at the? I mean, like watch that video that for the class that you missed on Monday. Because we covered chapter 5.
I know I did not get a chance to look at that because I've been trying. I'm getting stuck with the ones in the beginning. This weekend, all I was going to do was get caught up on all the homework and everything.
Yeah, please. Yeah, because that seems like we are piling up all the material in one on the other one like that. Keep piling up. Keep adding up.
Yes.
So now we are on chapter 6 actually today.
Okay.
Okay. What we did was that in chapter 5, pretty much, if I'm gonna just recap what we did last time, that we built up a certain model for one outcome variable, which gonna go to y-axis.
Mm-hmm.
Okay. On the y-axis, normally that we're gonna have the outcome variable or the response variable. It can be explained through another variable. Okay, we had that discussion up to a certain point, but here, instead of that going for another variable in the very beginning, yeah. Good evening, that Melanie. Yeah, what we did was we just started that. I was just going through that what we had been doing last time in chapter 5. In chapter 5, that we pretty much started with a model in which that we're not going to explain one variable, which is the outcome variable. Outcome variable is going to go to y-axis, and it can be explained with another variable called the explanatory variable. We had a broader discussion on that one, I think, in like that. But at that point, when we built in up the model, we just simply that utilize y variables average. We utilize the y variables average to explain that one, because we didn't use that any explanatory variable in the very beginning. Let's say that thumb length. If you have a thumb length, rather than it's been explained through another variable called maybe quantitative variable or that qualitative variable, doesn't matter. What we did was that we just trying to build a model based on that quantitative variable or the qualitative variable. But in the very beginning, we didn't add any of these explanatory variables. We utilized thumb length being explained through the thumb length average. That's what we did. Thumb length being explained by the thumb length average. So pretty much in that discussion, then we met something called that we built up the model. We say the y equals y bar. Y bar represented that sample mean average, which I talk about, plus some other stuff. Other stuff means like when we're going to estimate that there are some stuff being added to that one. That means that error term. Okay. The error term has been added to that one. Okay. So when that error term being added, we came up with a model with the kind of like a y equals y bar plus error term, like that. Now what we're gonna do during that error term playing a heavy role in this our discussion. Error term can be that we can check for the error for each and every data point. Okay. Let's say that what I'm talking about based on that one. Okay, but I'm gonna go ahead and then share this screen, the next screen. You can see what I'm talking about. Oh no, share this one. Yes, okay. On this one, this is what I'm talking about. So I have a population model and I have a sample too. The population is very abstract, very theoretical. The model is definitely going to build up for this guy, for everybody, all thumb lengths for that, all whoever that's going to be in that particular population at that moment. Okay, so for all these being, we feel like that they were fitting into a certain model. Okay, that's a certain model. Okay, we don't know exactly how it looks like, but we know for sure that when you pick a sample, based on the sample, you can easily draw a histogram, or you can get the summary statistics, or 5-number summary, or you can draw like a histogram. See, graphically you can see. Okay, we can fit in those data into a graphical representation called a histogram. If you have a quantitative data like a thumb length, you can put into this one. When you put into this one, we built some kind of that model. We're gonna say the data available equals to the model plus the residual. So residual means the error term. So the data being represented by y, error being represented by bar, residual being given by e. Its counterpart on population, we did discuss this one last time. Y, this is called the population mean. It's unknown. It's fixed. It has only one value. Average thumb length for all students, or whoever that participated in that particular, all individuals, okay? Their average, we don't know, it's unknown, and this is called the error. This is counterpart E, residual. And on the other hand, same thing being denoted by beta naught for a certain reason. I explained last time that it seems like we're going to have a data. We can fit this data into some kind of a straight line. We can get into a straight line later, but in a straight line, this part is called the intercept. See, it's like intercept. See, that's another way of explaining that one. It's the same thing, y bar or b naught, or sometimes we call the y hat. We had this very broader discussion on that one last time. That to that one, before I'm gonna come to this one, I want a little bit talk about that one too. Let me see. It should be somewhere. Okay, I'm gonna. Okay, sorry. It should be here in this one. See, the same thing that we discussed last time. That I recap that from one thing being doing. See, I explained that one in large scale in my video. See. Especially, see, population has a see. It's for the null model plus error. Y equals mu plus epsilon. In a sample, we pretty much the same thing of the estimated part. Null model part the residual is given by y bar. Y bar in as estimate for the mu. See, this is a population average, this is sample average. This is the population error, this is sample error. So in that sense, you can say, see, in the sample, see, same thing. See, I mentioned that one, same thing. I'm writing y hat, y bar, b naught, same thing for sample. See, again, another way of doing that one. See. So then sample that you can explain like b naught plus c. See, b naught plus c. See. See. Or that y hat plus c, or y bar plus c. See, several ways. See, there are three ways: y hat plus c, y bar plus c, b naught plus c. This is all the model. Why can be explained? See, since you have a data can fit into a model. Model means like some kind of a mathematical structure being utilized, built up by the mathematician and statistician for their convenience and mathematical tractability to tackle that certain kind of a scenario. When your data are available, they're gonna just fit into that particular model and see whether it's gonna fit into that one. If it's not gonna very well fit, we're gonna end up with an error. See, there would be an error incurred during this estimation procedure for sure. See, this estimation procedure, that error should be added to that one. If you don't have an error, you say your data perfectly fitted into this given model. Then you don't have the probabilistic model. Then you have a deterministic model, very deterministic. Then you don't need the statistics. Then you don't need the data analytics. Then you don't need the data science. You don't need the probability. You don't need the chance process. You don't need any of these if you don't have this error term. Because of this erroneous situation, it's going to become more probabilistic. It's random. Otherwise, it's deterministic, fixed. See? Like a thumb length can be fitted into the same model like that one. You get that the average of that one, and then simply you're going to say your thumb length equals to, see, the thumb length equals to the way that thumb length equals to the average. See, thumb length equals to average. They say that instead of looking for the thumb length for individual, can we take the average of those guys? That's what they were. That's what their physical interpretation of this one. They say why would be thumb lengths? They say don't go to thumb lengths of the each and every individual. You don't have to worry about each and individual. You can just summarize and then think about that some kind of a number that can be very well fitted, some kind of number that can be utilized as a model. See? Then if you don't have an error term, there's no any error. That means like whatever that you have that the average gonna be exactly the same as this one, then it's gonna be deterministic. But that's not the case that in this our discussion. Our discussion, we always have error. Even though that, let's say that you want to measure the height of some certain student or certain individual, you measure first time. Second time you measure, you're going to come up with not the same answer. There might be slightly different than the first measurement. That difference creates some kind of a statistical probabilistic model. That's how we get the model, because we are trying to minimize the error. See? At the end of the day, in data analytics, data science, and in statistics, mainly in statistics, we minimize the error. If the error has to be minimized. So we had that discussion abroad. Now we are mainly focused on, then later on we say that y bar is an estimate of mean. This in statistics, we call these as statistics. Whatever the characteristics, whatever the quantity that you're going to see over here, mainly that these, any summary. Summary means like, I mean like not the individual data points. They are summary. Let's say salary, they are average salary. That would be that summary, or the summary. Okay, height, average height would be summary. Their standard deviation, variance, kurtosis, skewness. So many things we have in this statistical arena, but we don't going to go through them in detail. But here in the primary stage, we just simply talk about only the average only. Okay, median, mode, anything. But fortunately that we have all the time, remember that in statistics or data analytics, everything comes like a twins, like a pairs. Look at the population sample. Population mean, sample mean. Population, the parameter, this is called the parameter, sample statistics. Anything that you're going to see in that sample statistics. These are parameters. Whatever is that available in all the quantities, all the summaries available in population or parameter. PP go together. See? Population means parameter. Statistics means sample. You're going to utilize a sample in order to estimate these guys. See? Statistics is a parameter estimate. So that in that today what we're gonna do, we're gonna that in chapter 6, that was in chapter 5. Chapter 5 we say that our model would be y bar only, because in the beginning that we thought that we have one variable can be explained by another variable. We just pulled back a little bit and decided no, we're not gonna throw another variable in the very beginning. We just used its own summary, which is average. Okay. In the very beginning, we are using its average. Sometimes we're going to call this one GLM model. GLM, see, general linear model. Some people, they call the generalized linear model. Okay, sometimes they say generalized linear model, but this is general linear model, because in the context of that scenario, sometimes they use generalized, but doesn't matter. Generalized or general linear model, GLM. See? This is the same thing I'm talking about. Same thing. This is, they put the I to indicate the each and every individual. Okay, so that's the same thing. See, same kind of a thing. We discussed this one. We discussed how we have some this thumb length. Their prediction. Prediction means like if data has not been collected, what would be that data point can be assigned for each and every individual if data has not been collected. Then you can simply say that's your average would be the predicted value. I'm not trying to predict another when another individual being added to this sample and see that the next student how its thumb length would be. Okay, I'm not going to check for that one. That's a different kind of a prediction. You can predict that what would be the next student's thumb length would be. That's same as this one too. In addition to not only that, the only people who already existing in the system, already in the system, their thumb length can be even predicted by the same average. See, look at 56, 62 predicted value. See, this is the projected value, 62. This is the projected value, estimated value, projected value. Like that. See, see, 62, 62, 62. Calculated value. These are observed values. See, these are observed values. Then the next one, you say that there would be another student going to enter into this survey or that into this system. That what would that can you predict that his thumb length would be? Yes, you can simply say 62. On average, it would be 62. That's a very fair prediction. Very fair prediction. Okay, that's another way to do that, or not only that. See, then we take the difference between these two. See, this is my y. This is my y bar. See, y minus y bar. See, y and y bar. See, sorry, I can show somewhere here. See, sorry, here, see, residual, see, y minus y hat, we call the y hat, b naught, y minus y bar. This everything has a physical meaning, means y means your data, 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 data. Y hat, b naught, y bar means estimated value, see, predicted value. Thumb means your value, see, data. Their difference would be this one, residual. Then we drew the histogram for this scenario. See, with the tiny fingers, we have only 6 data points. We drew that one. We saw that what happened to thumb length and residual. Look at their see, if you compare, contrast these two, you can easily see that how they've been distributed. See, this thumb length average. You know how to draw these lines. We discussed that one in last case. 3 data points. See, 3 data points are below the average. You know, which ones are 56, 60, and 61 below the average. The other 3, 63, 64, 68 above the average. On the other hand, if you go ahead and do the histogram for that residuals, see, residuals, its average would be 0. How come its average is 0? It's not indicated here. You add all these numbers, that would be 0 for sure. Residuals, if you sum them up, it's 0. 0 divided by 6 is 0. See, that's a 0. It is a fact for any data set. This is a fact for any data set. Okay? If you find the residual based on that given sample, on average, your value is going to be at 0, and then 3 values below 0, see, and another 3 above 0. And if you go ahead and look at these, the shapes, look like a fat, see, like a uniform shape. They both would carry the same shapes. See. But if you increase this one, this shape's gonna change. Okay, if you increase that the individuals, and if you come to that real fingers data set, these are definitely the shape's gonna definitely change. See? Then what they did was, see, they went to the residual and then they summed them up. See, this is the function, tiny fingers. And within that data set, you go to this variable, and then you use the function to sum them up. That would give you 0 for sure. By even looking at this one, you can tell. That tells us the very serious thing. That means that you cannot do nothing with the residuals. This is nothing. You cannot mold this data into any kind of a form. No, nothing can be done upon these residuals. Residuals that if you sum them up, 0. You have to remedy that situation. That's what we are trying to do in this chapter. See, you 0. See, then why is the sum of the residual equal to 0? Because the mean balances the residual. You know the reason. Mean balances the residual. Median balances the data. Median balances the data. We had that broader discussion. Mean balances this one. Not the mean balance the data. Mean never going to balance data. Mean balances what? Residuals. Residual means what? Your data minus, for each and every data point, data minus the estimated or predicted value. That's the reason. Okay? That's the reason. Now, because of this serious issue over here, when you're going to sum them up, in order to prevent that they are becoming 0, what we're going to do, we're going to take the absolute value. Go to each and see, you're going to take the 56 minus 62 and minus 6. Instead of minus 6, I'm going to get the absolute. Absolute means always positive. You put the positive value, 6. You take the difference, which is 60 minus 62, which is minus 2. You take the absolute value. See, that's what we are trying to do over here. This is the error. You can remember error. How do you write the error? Y minus Y bar. Now, error you don't take as it is. You take the absolute value of that one to make the sum make some sense. See, if you get this absolute value for this one, this becomes 6. If you take the absolute value, this becomes 2. This becomes 1. Then you have a 6 plus 2, 1. See, 8, 9. 9 times 2, see, 2, another 9 on this side, 18. See, otherwise, when you put the absolute value, when you make this every number positive, you're going to come up with a certain number, not 0. See, that's the very reason. This is the one of the remedy that we're going to utilize in order to avoid the sum of the residual becomes 0. See, sum of this residual becomes 0 is prevented by taking absolute on the residual. This is residual. That's the residual. See? That's called the sum of absolute deviation. You know, this is called error from here to here. Y minus Y bar means error. See, that's called the deviation, another name deviation. I'm going to read from this side. From this whole thing, I'm going to read from right to left rather than reading from left to right. Okay? I'm going to go from here. Deviations, their absolute value, okay? Then absolute value, and then sum. You get the deviation, then took this absolute value. This is parallel lines means absolute value, then took the sum. This symbol for the sum. You know that. See? So you're going to read from this side to that side. When you're going to get the meaning, it's easy if you're going to think about, okay, you go, see, you go the difference, residual, deviation, its absolute value, and sum. That's what we call the sum of absolute deviation, called SAD or SAR, sometimes called the sum of absolute residuals. Okay, I can show you that one. 1 second. Okay, let me see that one. Okay, give me 1 second. Okay, yeah, on this one. I have so many nodes, okay. I'm gonna pick the right one. Yeah, it's the same thing that we had earlier. So, look at what we did. See, there are several ways. Population model, my sample model. We can be written in different ways. Then I found the sum of residuals. Sum of residual is this one. Data minus the model. Always 0. See, residual. See, since this term equals 0, that means that residual sum of residuals are 0. We take the absolute values of residuals. See, we take the absolute value of residual. See? Residual of a point, yi minus y bar. Absolute residual at that point, absolute. Then we make absolute. First take the residual or deviation. Later on, we're going to get the absolute. Then you're going to sum them up for all the points. That's why we call the sum of absolute deviations or sum of absolute residual. Sum of absolute deviations or residual or sum of sometimes this is that's another one squared one. We're going to talk about that one later. This one, see? Sum of absolute deviation, SAD or SA. See? So how do you calculate that one? See? So see sum of absolute deviation, this one, or that one. I'm gonna talk about that one later. For time being, let's go and look at that one. See, if you have a data, let's say if you go to this data point, you're gonna get the difference of this one, get the absolute value 6. You're going to take the difference, which is negative, but you take the absolute value. That's called abs residual. You can, if you want, you can give another column, create and say abs residual. And this become plus 1, 1, 2, 6, and then add them up. And then you're looking into that value. That value is going to be here 6 plus 2, 8, 8 plus 1, 9. Not for this one. I'm talking about after you take in the absolute value, making this one positive. Another way, making this one positive. You're not going to square. But you take the absolute value, that's the way you can easily drop the negative sign, because you have to definitely drop these negative sign of these values to make sure that their sum would not add to 0. That's what we are doing. One way of dropping this negative sign is taking absolute value. Another way of doing that one is to make it a square. We're going to talk about that one later. Then we're going to see, take the absolute. These people, these numbers, they don't need the absolute value, but these ones, you're going to take the absolute value and then sum them up. You're going to come up with 18. Okay, that's what they are trying to do. That's what they say. See, deviation. Which part is deviation? This is this part. See? Y minus y bar. Okay, or sometimes you can say y minus y hat. Okay, or sometimes you can say y minus b naught. That's the same thing. That's the same thing. Okay, that's the same thing. That's the same thing. And then take the absolute. That means this one, see? Parallel lines in the beginning and at the end. Then take the sum. Sum is denoted by this notation. See? The expression above suggests a series of mathematical operations. Place them in their proper order in the target column. Take the absolute value. What's the proper way of doing this one? For each data point, subtract the mean. That's the first thing to do. For each data point, subtract the mean. You're going to subtract the mean from each data point. Same way we did that 56 minus 62. Then you got this one. Then you're going to take what? Then next step for each, see? Then take the absolute value. Then take the absolute value. Then take the sum across all rows in the data frame. Across all rows in the data frame. Okay. Across all rows, okay? That means you're gonna go down, see? Plus, see? And sum them on. That's the right procedure, see? So in this context, deviation from the mean means the same thing as the residual. See, I told you. Deviation, if you want, you can call the residuals. If you want, you can call the deviations. You can say the difference. Doesn't matter. But when you want to take that absolute value, you can easily take the absolute value of that guy by taking this, running this function, ABS abs. Whose abs? Residuals abs. See, they systematically converted them into positive values. See, that's what they were doing. See, as with everything, if we don't save it, this absolute value of the residual are lost. Okay, modify the following code to save the absolute residual in the variable abs residual. See, you're gonna create a new variable and add it into this data set. Okay, it's called abs residual. ABS, okay, capital ABS residual. How do you get that one? I'm gonna go to that, get this guy, and see. You're gonna go to the tiny fingers data. You go to residual to take the absolute value, and then take the sum. Whose sum you're gonna take? See? This one. Okay. Abs residual. See? Modify to take the abs residual. Yeah. See? You get the, you go to the residual, and then if you run even this tiny fingers, run the tiny fingers, I'm gonna put the residual and now you have this column. That's residual. You have a residual. That's residual column being added here. And then they're going to say sum these numbers. See? That would give you 18 for sure. See? It's a function to sum. Who will be summed? That's residual. Where? In this tiny fingers data. See? I ran this one too for me to see that clearly that here these are the figures. See? Like this. Okay. Now the same thing, to try to map the R function with the mathematical notation. Sigma. R function for sigma, sum. R function for this guy, receipt. Receipt. Can you remember? If you want a residual, you can remember it's already created this residual in this data set. This data set. It's residual. Already we took the absolute for that guy later, but in order to get the residual, you definitely have to use, you can easily use the receipt one. See? Receipt of the whatever that name of the model. See? That one. And then take this one. Sum is this one. See? Look at the mathematical notation being translated physically, and then there are codes. So the sigma, that means that the sigma, you can easily see that so this one you can remember that in the very beginning, tiny empty model. Can you remember how did you get that one? That means I'm talking about, see, before you come to this one, before you get the residual, they say that sometimes before go to that one, I can show you this one. See, this one before come to residual being added to that tiny data set. See, you run this one first. How do you run this one? Can you remember? Its name has been given. You ran what? With the LM. See? LM, linear model. You ran the model with this one. Then you put Y. Y is your what? Thumb. Okay. Thumb. Okay. Then tilde. Can you remember? When you put null, then you were talking about the data. Data is the tiny fingers. You wrote like this. Tiny fingers. Now we save that one to something called tiny empty dot model. See, tiny empty dot model. See, tiny empty dot model. See, like that. Save to that one. Now, if I want its residual, residual coming from that means y minus y bar. Automatically, the program will calculate our residual. I'm talking about this column. Okay, how we got this column? I'm trying to get this column. See? And then we go to the same tiny fingers data. See, tiny fingers, and I'm gonna create that one. See, tiny fingers residual, they already created. How we got this one? I'm here now. See, I'm not talking about these three, but I'm starting from the very beginning and writing over here. And it's coming from taking the residual receipt on whatever the model you have, this tiny empty model. We call that one null model, empty model, because no other variable has been added still. Okay. See? This is how you got the residual being added to this one. Now they say from that one, once you have a residual like that, go to now again inside this one and take the absolute of that one. That's the step that I'm doing here. See? That's how I got that variable being added to that one. See? Now I'm not interested only in the residual. Whatever I got the residual in that particular data set, I'm going to go to and take the absolute of that. And not only that, go and then sum them up. See? Go and sum them up. See? And if you want it, it can be even assigned to something called sum. Or you can give a very good name for that one. You know what's the name for that one. You can say sum of absolute deviation, SAD, see? Or sum. See? You can do like that. So, see? It's not going to come and stay over there because we are not planning to put that back into that because it's not going to stay in the data frame. But this has gone inside the data frame. Residual had gone inside the data frame. See? These are the 4 steps. Those are the 4 steps that that's how you got this guy and this guy inside the residual this data set. See? In addition to that one, how we got the predicted value? Can you remember? Predict. We can get the predicted value as well too. See? But you don't need to. We did that one in 2 ways. I'm talking about this residual can be easily calculated through this function. Or what we did was we created the predicted value. We already have this data set, and we found the difference between those two. That's another way of doing that. We had that broader discussion in last year. Okay, don't make any mistake or anywhere, because to make it very clear that what we are doing over here. Okay, I'm sorry here. Like that. See, several ways we can get this done. So this is how up to this SAD one came. I'm talking about up to this one. They were talking about when you have mathematical notation, how that can be translated or explained through explained through this function. See? Yi minus y bar explained by rest. See? This is it. Then y minus y bar, that's receipt, and absolute. If you want absolute, just go ahead and do this. Whose absolute? Residual absolute. Okay. Now see, if you had to write the one line of code to represent the sum of absolute deviation, SAD one shot. See, you don't have to go. See, you can write everything in the same thing. See, you go to receipt, you go to abs, you go to sum. This is nothing but okay. This is if you want to run this one shot. Okay, that means okay. I'm gonna make this one shot rather than. So, okay. So I'm talking about this one. See? I'm talking about SAD. Let's say the sum of absolute deviation O, sum of absolute residual, which is given by mathematically y minus y bar. Like this. This one, the R code would be one shot. You go to sum. See? That for this one. Then inside you go to abs. See? That for this guy. And inside you go to receipt. Receipt means like this gap. That gap. Receipt of whose receipt? That model. Okay. Tiny empty model. Empty model. See, like that. Close it because we open that one. See, 1, 2, 3 open, 1, 2, 3 flows like that. See? Okay. You can one shot like that. See, whatever we wrote over here, see, this whole thing, see, when it came to the SAD, I wrote how many lines? See, 1, 2, 3, 4, like that. You don't need, you can one shot that. See? If you really want to put them back into that, this data set is a different thing, but if you want to calculate, this sum abs residual given by residual, and then put the model. How do you get this one? Then I'm gonna write another one inside this one. Okay, look at this tiny empty model. Tiny empty model you can run inside. See? What is the tiny empty model? See? You can say sum abs residual. Whose residual? See, you can say your thumb. See, I don't say that empty model. Thumb tilde null, see, comma, data equals tiny fingers. Close it, close it, close it. See, that's another way of writing. Same thing. This is SADO, sum absolute, sum of absolute deviation or sum of absolute residuals. That's another way of writing. I think one shot you can write. You don't even have to go to empty model. Empty model you can call over here. That will give you the SAD, which is 18. One shot. Okay. 18. That means just try this one. See. Sum abs. See. Sum. Okay. Abs. See. Then residual of tiny empty model. See. Tiny. Tiny empty dot model. And close it, close it. Some apps receive tiny empty model. I'm talking about that what is it? Tiny empty model. This one. Okay. And then 18. Last one. So let's say instead of that one, let's see that this one. I'm gonna take this out and then say thumb tilde null data equals tiny fingers. Should work. It looks like a looks like a day. It doesn't take that one. Yeah, it should work because when non-numeral area because of this residual is the issue. So if you put because of it should work. Null and data. Let me see. Null data tiny should work. It's right here. This one doesn't take. But when I ran that one, it ran. I will see that it's not wrong. Absolute receipt. residual of yeah, the inside the argument here, inside the argument, this one, it should work, this one. You see, because of this one, this is the issue. Okay, I'm gonna take that out. It should work, but when I ran that on work, but it seems like I had to look into that one. What happened? It seems like you have to this one first. Non-numeric argument. The mathematical function, because it is a mathematical function, it is a non-numeric argument. That's why they say it has to be this, because when we write like this, it doesn't take like that, because it has to be numeric value. See? Numeric value one by one, they have to take it. Then if I put with the y tilde, it should take. I had to look into that one, but earlier when I was running it came on. Okay. But anyhow, that at least that this first one, some absolutely this receipt of, we're gonna take tiny empty dot model. So this one, right? See, even that, yeah, this should work because that, but it doesn't take like this way. I think that I have to look into that one because I ran this one with like a different function using different function with data. But anyhow, okay. We take tiny empty model, you run first and then you can put this into inside and then run farm apps receive everything together. Okay. Then what we're gonna do that we're gonna go further down and then pick another one, call that absolute. As I said earlier, in order to drop this negative sign, you can drop the negative sign by taking absolute value or taking the square. This time we're gonna take the square. Instead of taking that, called the square deviation. Okay. Sum of square deviation. Okay. Normally in this one here they are using SS, but SS not enough. SS gonna go with the sum and squared only. See, S stand for the sum, this second S for the squared. There should be either D or R, sum of squared residual or sum of squared deviation. Okay. So I'm gonna, when I'm gonna write like that, sum of squared deviations. Okay. So this is what I'm talking about. I'll show you. Okay. This is what I'm talking about. See? Y minus y bar, now I'm gonna square. This one said sum of absolute deviation, sum of absolute deviation. This one sum of squared deviation. That's how you're gonna do. Sum of squared deviation. You're gonna square this time. This should be SSD, not SS is not enough. Okay, because there are other quantities we're gonna introduce too later on. Okay, or SSR, sum of squared residual. Or you can read from this side, residual sum of squares. See, either you're gonna read from left to right or right to left, still you can get the answer. See? Okay. Residual sum of squares. Some people they read like that. Residual sum of squares or sum of squared residual. The same way, see, sum of squared deviation. See? Or you can say deviation, see, sum of square. Deviation, sum of squares. Either read from this side to that side, doesn't matter. Okay. So SST and R, those are the two ways of doing that. Look at what happened. You know that. We don't do anything, no remedies. You're going to get the deviation or residual, sum of residual. This is sum of deviation, SD only, sum of residual or residual sums or deviation sums. See, always zero. Sum of deviation or sum of residual, see, adding up to zero, see, zero. That's why as a remedy we took the absolute. Then you got the sum of absolute deviation or sum of absolute, say, or you're gonna square. This time you're gonna sum of squared deviation. That's another way to remedy this situation. This is very useful. Sum of squared deviation. See? Sum of squared deviation of sum of squared residual, SSR. Or sometimes I can put here to say to another way of writing this one, sum of squared error. Because of the certain reason, you can, if you want, you can say SSE, sum of squared residual or sum of squared error. You can say that would be error. That means that this one, you can add another one, say sum of, oh, not this one, so was in the wrong book. So, yeah, so this one, sum of squared, there should be R here. Sum of squared R residual, okay? Or sum of squared error, okay? See, this is the way you can remedy that one. See? So that's what they were trying to do at the second stage. See? Second stage. See? Now they're gonna square. Now they're gonna square. If you square those numbers, see, you're gonna go to the tiny fingers residual and square. See, this is the code. You can see that whatever you had here, minus 6 square, you get 36. Minus 2 square, you get plus 4. Minus 1 square, 1. 1 square, 1. 2 square, 2. 4. 6 square, 36. See? That's how you get the numbers. How do you get that one? By simply doing this one. Now they say save the squared residual to SQR residual. They have given a name. That means take this guy and then save to this guy. Then it's going to go to the same data set. And then now run. Or now find the sum. Sum of whose sum? See? Whose sum? This guy's sum. See? This guy's sum. It's going to be 82. 36 plus 36, 72. See? 72 plus, see? 10. 82. 82. And you're going to square like this, see? Caret and put 2. See? So sum, this is for sum, this is for deviation, see? Recede again, this is for square, see? That's an R gonna use this one, R gonna use this one, R gonna use this one. Or the same way that one shot you can do the same way that we did earlier. You go to sum, you go to recede, see? It's gonna square and then sum, see? Sum comes after this one, okay? That's why I have 2 parentheses, okay? See, I'm gonna open it, close it. Before I'm gonna take the sum, I have to square, okay? You're gonna take the residual of this model. Then you go put a parenthesis and then square and then take that one. Not gonna work, see? See, look at that, it's not gonna work. See, it's not gonna work either, see? Look at it. Should be that, see? You have to make sure you take the sum first, okay? That's why this is the right one. Sum has to be, because you do the square within this one, see? Go to residual, empty model, and square that one. See? This one you cannot take, this one absolutely, and this one not at all. And out of these two, you can see this is not going to work because if some you have to do the residual. Sorry, residual square. Go to residual, which is up to here, and square the residual. You're not squaring this guy. Okay, if you square this one, it's going to come inside parentheses. You square the residual. Okay, this is what this means. Okay. You go here, empty model. Okay. You take the residual one, that one up to here. See, to here, residual and the square. See. Look at it. It's the simple model of our tiny finger data was a number other than the mean 62. Then which of the following would be true? See, the SS is bigger than the SS for the mean. See, that means, see, SS bigger, sum of squared what? See, sum of squared deviation, the way that they are using that SS, see, SS means sum of squared deviation, sum of squared deviation, see. Sum of square deviation, because how far that each and every data point is deviated from the average. That's another way. See how far that. See how much would that be? See that deviation. You have a serious issue that you cannot add all the deviation. That would add to 0. Then you get to the absolute value of the deviation, or you're gonna square the deviation and sum them up for. Sum means like you're gonna take into account all the data points. Sum means you're going to take into account all the data points and look their deviation and then add them up. Okay. So here they say SS is bigger than the SS for the mean. See? If the sample model of our tiny finger data was a number. See? If the simple model of our tiny fingers data was a number other than the mean. See? Other than the mean. Then which of the following is that one? What that means? What is they are trying to say here? It's very interesting what they're trying to say. They say that instead of that mean, if you by any chance pick another number to model this data set, which one will give you the sum of squared deviation or sum of squared residual? That means this is what I'm talking about. This is exactly what they're talking about here. They say that, okay, let's say that this is my model. Okay, I drew the histogram. Okay, your mean gonna be somewhere in the middle. See, this is my mean. Instead of that one, with respect to this mean, I can check all the residuals. With respect to this mean, you're gonna subtract that the gap. Your data point is gonna be here. Okay, if I show with this one here, that is the new one. That this is what I'm talking about. This is. See, this one, let's say that this is y, here this is y bar, okay, this is your thumb length, okay, for my convenience I'm going to go like this way. So what are the points that we have? We had a 56, 60, 56, 60, 61, 63, 64, 68, okay. So we have 56, I'm going to show you, okay. 60 we have a 61, then we have a 63, then we have a 64, then we have a 68. So y bar would be 62. This is what I'm talking about. Okay. They say that these deviations, see, deviation for this guy was residual for that guy, residual for this guy, residual for this guy, residual for that one, residual for this one. See? Residual for this one is plus 6, you know that. Residual for this one is plus 2. Residual for this one is plus 1. This one is negative 1, negative 2, negative 6. Is that 56? Yeah, okay, good. See, those values. I'm talking about these values. See? This one, residual, 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 residual. See, they say that if you add all these residuals, okay, you're gonna add to 0 for sure. Then you're gonna square this one, square, 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 square. That one we call the SSR or SSD, or in the book they call SS. Or I have another name for this one too, SSE, SS. Sum of squared residual, sum of squared deviation, sum of squared error, or simply they call SS in textbook. It's the same thing. They say that if you do this one with respect to this one, or rather than do with respect to y bar, which is 62, I'm going to pick another line, another one, not a 62, different number, thinking I'm going to pick a different number. Let's say I'm going to pick 61, thinking that my number would be 61 line. With respect to that one, okay, same data points. You have a 56, see? You have a 60 here. 61 going to be definitely on the top of that one. And then you have a 63, you have a 64, you have a 68. If you have like this, if you take that at this gap, see, 56 minus, see, 61 minus this one is negative 5. See, this one is negative 1. This is 0. This is plus 1. This is plus 2. This is, see, plus, no, I'm sorry, plus 3. Plus 3, this is 2. I'm sorry, 2, 3. Okay, this is 3. This is 3. And this one gonna be 7. And if you're gonna square this one, you have this one, 3, square this one, square this one, square this one, and square this one, and get the new one. I'm gonna call that one SSR star, or SS error star, or SSD star, or SS star. If you calculate that one, they say this value, you can check into the value. Look, you can calculate this value earlier. This value is what? 82. Let's check for this value now. See, negative 5 squared plus negative 1 squared plus 0 squared plus 2 squared, 3 squared plus 7 squared. You get 25 plus 1 plus 0 plus 4 plus 9 plus 49. How much would that be? Would that be smaller or larger? That's what we want to know. Look at 49, 25. See, 25 plus 1 plus 4 plus 9 plus 49, 88. 88. They say that's why if you calculate for the model, if you use a different number than this one, your sum of squared residual is going to be getting larger. Larger means larger variation. Larger variation. In that sense, for this 82 coming from that's the minimum variance. This is another name for this one too. Another name for this one too. We can call the variance. Variance or variation. See, another name. The variance here is another variance here. Variance. Star. See. So they say that the variation calculated with respect to the sample mean has the minimum variation than being the same variance being calculated with respect to another number. So that means your SSR, I'm going to go with SSR, always less than SSR star. So this one is 82, this one is 88. See? Another way that they found this is the minimum, see, SSR that you can calculate. Any value you pick rather than the average would produce larger variation. That's what they say here. Okay, that's what they are trying to say. See, that's it. See, SS you calculate with respect to another number, different number other than the means. That's why I picked the 61. With respect to 61, if you calculate the deviations and then square and then find the sum of them, that would be definitely larger than what you had done with respect to the mean. That's what they say. Okay. So that's a very interesting thing. That's very, very interesting thing, because this is coming from is coming from a certain theorem called the Rao-Blackwell theorem. Means minimum variation come through the definitely this. If you calculate the sum of squared residual with respect to mean is playing a heavy role. Okay, that's what they try to say. See, now they come and talking about the beauty of the sum of squares. They're talking about that, as I say. See, now finding the sum of squares. Sum of squares. See, not one thing. How do you find the sum of squares in this? See, if you run certain thing, you can easily get sum of squared rather than do by hand. Now we're gonna come up and then you're gonna run this one. We know that is called tiny empty model, and you run ANOVA. See, ANOVA. It's called the analysis of variation. ANOVA on that model would give you this table. That table show you, see, sum square of residual. See, sum of squared residual is nothing but 82. Very clear. Another way of getting this one. The way that we did earlier, it's a long way of doing that one. You can remember how we were doing that one. See, here what we did was, see, we went over there. I'm sorry. We went to this one, see. You square that one, see. You square this guy. You went to the, you ran the model. Then you go to that, you get the residuals, and then residual square, and then find the sum of that one. Okay. First, you have to get the residual. See, by even though you are running that everything by a code, because you are running the code in order to go for that rather than go one by one. But it's still that there's a process, because in order to get the residual, first you have to get the residual. How do you get the residual? We already discussed. What's the code for get the residual? We discussed. 2 ways you can get that one. And put it back into the original data set, and you go back to the data set and say, hey, I don't need the residual. Now square and then put it back into another variable called the SQR residual, and then you find the sum. Instead of going through in this this long way, okay? I'm talking about this one, see? Sum, abs, receipt, tiny, empty, like that way, the way that this way, you can get this done one shot by running that model through this ANOVA. If you run ANOVA for this model, that would give you this table. Its table name is analysis of variance. That's why we call analysis of variance. Is an acronym. See, ANOVA, see, table. The response. Response means what? Outcome variable. Another name for outcome variable, response. See, yield. Sometimes we call the yield. Response. See, that's thumb. Then you have a residuals. You have a very interesting thing called the DF. DF stands for the degrees of freedom. What that means? See, degrees of freedom, DF. DF, for sometimes we're going to write like this, a DF. Degrees of freedom. See, that means number of independent pieces of information utilized to estimate unknown parameters. When you have a parameters, you can remember you have a parameters in the population setting. Those are to be estimated. Then when you estimate how many pieces of independent information you have in your hand, called the degrees of freedom. Okay. Here, degrees of freedom is 5. How do you calculate the degrees of freedom? It's calculated like this way. N minus, N stand for sample size, minus, I'm going to write here very clearly, number of parameters to be estimated. In my case, I have 6 data points. Subtract how many parameters in my model. Look at my model. Y, I can remember my model. Y equals data node plus epsilon. This is my original population model. See, population model. Can you remember? Its counterpart, you wrote like this way. See, you wrote like this way. Y equals B naught plus E. That's the same thing we call the, B naught O Y bar, see, plus E, or Y hat plus C. That's the same thing. Can remember. Or the same way, this can be written the mu plus epsilon as well. See? So look at here, one parameter 1 only. Because of that, I'm going to subtract 1. So therefore, I got 5. If you have a 2, you subtract 2. Okay, that's how you got 5. See? This has to be estimated. Yes. Did you estimate? Yes. What is your B naught? Y bar. Okay? Y bar. Sample mean. Sample mean. Instead of that one, you can think about that population mean plus the epsilon. What's its estimate? Sample mean. Population mean best estimate would be the sample mean. We know that one. See? That's how we got 5 here. 82. How we got 82? We know that. We know how to get 82 in another way, in several ways. Then the mean SQ means like a mean squared residual. See, this is called a mean squared residual. See? This means that on this ANOVA table, we can talk about several things. See? We can talk about this. See? You're going to say that this is the source, another way, source of variation. Okay, source of variation. I can say source of variation. Okay. And then I put the degrees of freedom. Then I put the SS, sum of squared. I don't know, sum of squared, textbook use only SS, but SS stands for only sum of squared. Whose sum of squared? That's how we put the residual here. That's the only variation we have. And other one is called an MS, mean squared. Okay, this means mean squared residual. This means sum of squared. So how do you get the mean squared? Very easy. Mean squared residual, mean squared residual is sum of squared residual divided by its degrees of freedom. Very easy. So in this case, residual is 5. Sum of squared is 82. How do you get the mean squared? 82 divided by 5. See? So this is that's 16.4. 16.4. The other one is F. We're going to come to that. Those are later. F is called the F value. The last one is called the probability PR greater than F means it's called the P value. We're going to talk about those two later. See, for time being, we're going to stick our discussion only to these three only. See, so this one we can easily find too. Okay, but we're going to come to those later on. Okay, these two we're not interested right now. See, so see. So you can get that by using ANOVA. See, that's why they say create an empty model of thumb length from the fingers. See, to create the empty model, you can remember how you create. See, ln tilde thumb, sorry, not tilde, thumb tilde. See, y, that's a y value. See, null data equals tiny No, not from the primary fingers. Fingers can do that one for the fingers. See? Now we do for the full data set. Fingers, and run ANOVA for this guy and see what's going to happen for the whole data set. See, 156. See, we have a data. How many data? 157 minus 1. That 1 for this one. 1 to estimate the population parameter, which is mu of beta naught. See? So this time we have 157 minus 1, which is this one. How do you get this one? You can remember sum of squared residual. See? You're going to read sum of squared residual. Sum of squared residual, SSR. This is mean squared residual, MSR. See? MSR. See? Mean squared residual. Mean squared residual is sum of squared residual divided by the degrees of freedom, which is here 16 points. This is mean squared residual. See? This one. Mean, on average, then you're going to find the mean for even for the sum of square residual. See? Even for the sum of square residual, you're going to, on average, how much would be? It's being divided by the independent pieces of information that can be utilized in order to tackle that data now. 156, 11,883. Then in order to get this one, you're going to divide 11,880 divided by 156. That would give you this one. But that program is going to run anything and give the value. Okay. On the other hand, that if you need this one, see, rather than that, if you need this one, you know how to get this one in another way. I'm talking about this guy. No? See, can you remember how to get this one? Sum of square residual, you can get another way. What's the other way of getting this? You're going to go to sum. Whose sum? You go to resid. Whose residual? Find empty model. Empty dot model. Okay. Empty model. Then square. Okay. You can find that one. Empty model. Then square. Then close it. Would that give that one? See. Resid of empty model. See, same value. It has been rounded to that only the integers, but if you want to run that one, you can get this way too. 11,880.21. But if you want to get that one easily with other information, you run that one with ANOVA. In any scenario, you have to make sure you're going to run the regression, run this model first, and then assign that one to some kind of a R object. And get that way too. We got an SS means here they are calling SS means SSR, okay, SSD or SSE, okay, I made it very clear. What would it be attached to, what unit would be attached to this unit? Square millimeter, square, because it has been squared, okay, it's very clear. Which of these lines of R code do you think would give you the SSR? See, we already talked about that one, see, another way of doing that one. Try running this code and see what the result is. Try running this code. Will this result in the same answer? See? That's the same thing I told you. Yes, it should be. See, 7,800. Get that one over. See, we did that one. See, this line up with the output we got from the ANOVA. See, ANOVA through the ANOVA function. Or through this one, you can easily get this one. Okay, that's why you have to make sure before you're gonna run this one. But here there's another one called supernova. You're gonna use the supernova because later on when you get more information. At this stage, you don't need the supernova. If you haven't that installed, all the packages. Make sure that in the very beginning I talked about several packages. They would carry that so many functions, that necessary functions for us to that do the calculation easily. Make sure you're gonna install all of them. Okay, that's another one for the supernova too. Okay, look at the variance. Now they're gonna talk about the variance. See? Okay, look at here. We say that sum of square is a good measure of the total variation. See, sum of squared residual is a good measure of the variation. See, as I mentioned earlier, we're using the mean as a model, but it does have one important disadvantage. Let's see what that would be. See? Look at this one. See, this is the outcome. See, see, first one, second one. See? Consider this distribution. Okay, see, assess from the mean distribution 1 to 14 some of this, which looks more spread out. Which look more spread out. See, if you go ahead and look the spread, that means how they've been distributed among about this mean, about the mean. They look the same. See, spread out the same. See, spread the same. But of the distribution of which has the largest sum of square? Distribution 2. Why? You know the reason. Why this look the same? Look at the spread out. It's a good sum of squared residuals can be utilized in order to talk about the variations. Variation is the spread. Look at the spread. Spread means to say how they've been spread out. See? Look at the 6, 6, 2, 2. They're gonna see. But if you go ahead and see that how many data points, see, at this stage only 1. At this stage you have 2. For 2 you have a 2, 1. Here 2 for 2. See, 2 number. Number 2 has occurred 2 times. Number 1 has occurred 2 times. Instead of number 1 has occurred 1 time and 2 has 1. 2 has only 1. So look at this one. Number 3 has occurred 4 times. Here 2 times. Here 6 has occurred 2 times. Here 1 time. That means this will contain more data points. How many data points? 2, 4, 8, and 10. Here 1, 2, 4, 5, 6. But they are spread out, look the same. But if you go ahead and calculate each and every data point, subtract from here, see? Subtract from here, see? Deviations. That's spread out the same. But the sum of squared residual would be the more for this one, because of that in the equation, and you can show that you're going to do this difference 2 times. See, here you do the difference only 1 time. See, because of 1, frequency 1. This difference you do 1 time. Here we do 2 times. This difference you're going to do only 1 time. This difference I'm going to do how many times? 2 times. So see, which look the more spread out? See? Look at here. Now the other way around. Okay, this case even worse. See? Although you can see the spread of the data point does not look different between the 2 distributions, the one of the bottom number 2 has a much larger SS. Okay, we are talking about this one. Okay, then again look at here, the spread, larger spread for the second one. See, distribution 4. Really spread out. But of the distribution of which one you really mean would be the better model? Distribution 3. Why? It has a smaller variation. See, the variation is small. Here, if you go ahead and look here, see, same variation. See, same spread, same spread. It's another kind of a distribution, but it has been centered around what? This number, same number, but here more data points are towards the tail rather than at the body part. See, more towards the tail, left tail and right tail. Here in the middle, clustered in the middle for this distribution. But the spread Spread means like every data can be captured, see, through the spread, larger spread, smaller spread. See? For which do you think the mean would be a better model? See? So that's why, because it's an average variance, is not impacted by, see, because it is an average, okay, variance is not impacted by the sample size and thus can be used to compare the amount of error across two sample different sizes. The variance, see, here I'm going to go through this one in little bit detail. See, sum of squares worked fine as a way to quantify error around the mean. It's a sum of squared error or sum of squared residual is the best way to quantify error around the mean and compare error across two distribution when both distribution had the same sample size. See? Same sample size. Here look at it. Same sample size, okay? But SS isn't easily interpreted when the sample size varies. See? Both distribution, when you're going to compare two distribution, both distribution at the same sample size, it's going to be very good way to quantify that error. But when the sample sizes vary, it's not. The reason for this is that each time you add another data point to the sample distribution, you are adding another deviation from the mean to the total sum of squares. That's true. So even if two distributions appear to be equally well modeled by the respective means, they may have very different SS. SS always grows as the number of data points in the distribution gets larger, irrespective of the degree of spread. See? We're going to see, you know that because of the larger number of the data points, you see, sum of squared residual, SSR, SSD or SSE getting larger and larger. See? But looks the way they see, spread look the same. But their sum of squared residuals are different because of the number. You see? If the numbers are different, sum of squared residuals are different. Sample size different here and here. Sum of squared residuals are different. See? Here again. On the other hand, sample sizes are different, and then their sum of squared residuals are different. And then if you check the sum of squared residuals, this one would create like a smallest sum of squared residual, while this can create like a larger sum of squared residual because of the spread. And on the other hand, look at the spread. More spread on this one than this one. Here look at spread the same, but different sum of squared. Different sample sizes, different sum in between these two. I'm going to compare and contrast these two distributions. Same mean, different, but sample sizes different here and here. See? But the spread the same. Spread the same. See? Then sum of square residuals are different here. Sample size different if you're going to compare these two. Spread different, okay? Spread, if you go ahead and check the spread, that would be different in between these two. Plus, sum of squared residual going to be different too because different sum. Okay? All these three things going to different. Spread, residual, sum of squared residual, SSR, and variance. The number, sorry, sample size. Okay? Sample size different, spread different, and SSR different. Okay, then see, that's what they say. Interpreted, see, but it's not. The reason for this one, blah blah, right? Okay. This problem is solved by adding two new statistics to our toolbox: variance and standard deviation. See? Now instead of that one, we barely mention that variance in SSR, but we're gonna make it like a very like a concrete, solid definition over here to calculate to solve this problem. Problem means like the problem when you're going to add more numbers, more data to that sample, your SSR going to change. To prevent that one thing, you can add, you can talk about two quantities. See, standard deviation, variance. Variance is mainly what we're going to talk about. Then its square root would be standard deviation. To calculate variance, we start with the sum squared residual or total error. See, other name for that one, total error. But then divide by the sample size to end up with a measure of average error around the mean, the average of the square deviation. See? That's another way it's called, the average of the square deviation. See? That's the square sum of squared residual or sum of squared deviation divided by degrees of freedom. See? Degrees of freedom. See? So therefore that this gonna be, see, look at the formula. This top part is nothing but sum of squared residual, see, sum of squared error divided by the n minus 1. They denoted this by s squared, see, s squared. See? Where is ss in the formula above? See, the top part. SS means they call the SS for the sum of squared residual. This whole thing together, if you divide that sum of squared residual, see, from this n minus 1 in this scenario, you can remember, if I get back to this one, sum of squared residual divided by degrees of freedom. I call that one degrees of freedom nothing but n minus 1. See, here n minus 1. In this scene, because we have only one parameter, that is nothing but mean squared error. So this means this is nothing but mean squared residual. That's the sample variance. See? Sample variance that can be utilized. See? It is not impacted by, see, variance is not impacted by the sample size. And thus can be used to compare the amount of error across the two samples of different sizes. You can compare and contrast and see how much the error would be for the different sample sizes by looking into the variance, because it is an average. Average, see, because it is an average, variance is not impacted, because variance is an average. See? This is the variance. Whose variance is that? The y, thumb length variation, the variation of the thumb length. See? Thumb length. See? Is not impacted by the sample size. See? So that can be used to compare the amount of error. Error can be, this is nothing but the error, because here we have a serious issue. We cannot compare and contrast this one, see, because of the different sample sizes. I was thinking that in order to compare that error incurred in this one and this one, when you compare by looking at the SSR, see, and compare these two, and compare and contrast these two with the SSR. See? But it's not a good way, because when you use the SSR here, you saw that what happened. If you use the SSR here and here, the variation is the same. Look at the same. But your SSR are different. So that would not be a good way to talk about the variation. Look at. We think that the sum of squared since that SSR going to affect by the what's the sample size. It's being affected by sample size. It might going to change. The variation is same. See. So what's the point of that? How could we going to differentiate these two there and see what would have that more error? See, look at that. See, if you go ahead and check the error or variation, see, the same. Here on the other hand, more variation, but the sample size, but the SSR different. Okay, that's not good way to look at it. Instead of that one. That's why we say sum of squared work fine as a way to quantify error around the mean and compare error across the two distributions when both distributions have the same sample sizes. If they have the same sample sizes, that's okay. But when you have the different sample sizes, you have to make sure that you're going to use a different kind of a quantity called the variance. Variance is nothing but mean squared residual. I'm trying to say the same thing. Mean squared residual. See? It's the same thing. Mean squared residual is sum of squared residual divided by degrees of freedom. That's the same thing. This is SSR, you know, this is SSR, okay? Degrees of freedom. Now I'm going to call that one a name, variance. See? Mean. So variance is nothing but, see? Variance, nothing but, see? Sum of squared residual divided by n minus 1, sorry, degrees of freedom, ds. Same thing, mean squared residual. Okay. So the way it's denoted by simple S squared. So from now on, I'm going to use this one, S squared. So this means like a SSR divided by degrees of freedom, or mean squared residual, or mathematical notation wise, y minus y bar squared divided by n minus 1. Same thing. Okay. Oh, you can remember how we got that one on the top part. Sum. See, if you write the R code for this one, I'm going to write this one two ways. Okay. I'm going to do this one, that part in two ways, two, three, several ways. Okay. Okay. Let's say that this one you can get the top part, you can get the sum. See, then you go to what? Receipt of that empty whatever the model. Okay. Empty model. And square close it and divided by what? N minus 1. One way. The other way, you can run the ANOVA on empty model. That would definitely give the whatever you want. Yes, this one. The same thing. Now its counterpart called the standard deviation. Standard deviation. I'm going to denote this by SD. Okay. SD is sometimes for the variance I use the var down the road. SD is nothing but then the square root of this one is that is S. That means you are looking for the square root of SSR divided by degrees of freedom. That means you are looking for square root of mean squared residual. So another name for this one we're going to call root mean squared residual. See, you can say like that, root mean squared residual. See? That's another way. That's the standard deviation. That's the second one. This is the first one. Okay. To check that the variation or that error across this all data. See? Variance is not infected by sample size and thus can be used to compare the amount of error across two samples of different sizes. Different sizes doesn't matter. See? You can utilize this. See? That's nothing but the mean squared error. That's what we're talking about. That's coming from the ANOVA table. See? This table, I think last time we had that one. Okay. Sample. See? Is this a sample statistics or population parameter? It is in sample. This is definitely sample statistics. Okay. Sample statistics. Okay, see, you can, on the other hand, you can get the variance of that guy and compare and contrast. See? Okay. This is a variance of whose variance you might be thinking, whose variance? Variance of y, okay. This is a standard deviation of y. Okay, y. So in that thumb length case, if you go ahead and that thumb length, you can calculate that your variance in another way, as I said earlier. See, I'm going to put this one to here too. This one, see, another way of doing this one. You can go to var. See, var. Use the var, the function. Okay, var function. Okay, it's a lowercase. Sorry, this one lowercase. See, var. Yeah. Then who's var? You go to, see, straight go to tiny fingers and go to thumb. You don't run that, you don't have to run that one. You don't have to run the model. Tiny fingers, go to that one and go to thumb. See? You can remember you got this one, see, either doing this way or this way. If you go ahead and get back to that, what we had 16.4, okay. How they were doing that one to fingers. Okay, I'm gonna go here. See? 16.4, I told you. That's the mean squared error. See? That's the same thing. See? If you go to the mean squared error, mean squared residual. See? How do you get that one? By running ANOVA table and read mean squared residual, which is 16.4. See? Or if I run in this one, you get 16.4. See? Or you can remember sum of resid is how much? 82 divided by 5. 6 minus 1. I'm going to write it clearly here. N is 6 divided by this one. 6 minus 1. You get 16.5. See, this way, 4. This way, this way. See? Same thing. We're talking about the same thing in different ways. Okay? Talking about here, okay? Here. This one will come further down. This one here. This one. It's one way of doing that. It's another way of doing that. It's ANOVA table is another way of doing it. You can end up with the same thing. Same thing. That means that we are trying to find the estimate for the sample variance, sample variation. It is already there. It's already there. We can calculate that in different ways. See? Now we're gonna do this one for the full data set. Okay, let's see that one what we can do for the full data set. Okay, that's for the tiny fingers. Okay, now again they're gonna say create an empty model of the thumb length from fingers, not from tiny fingers, fingers. Linear model LM. Then you have thumb tilde null model. That's for the X. You put that one. Data fingers. No? Fingers. And then run ANOVA on this one, empty model. Okay. Okay, LM data fingers. See, 76. Mean squared error 76. Mean squared residual is 76.155. Okay. So then the square millimeters, we know that we have to square that one. The same thing you can get it from this way. We know that one too. Okay. See how to get that one? See, run and see. You're gonna get the same thing. Sum of squared error. I'm talking about this guy. Okay. This one divided by this one will, as I mentioned over here. Once you get that one through some receipt, that value should be divided by. This is not 61. I'm sorry. This one 6 minus 1. All right. 6 minus 1, which is 5. So that way you can get that way and divided by 5. It's the same thing. Get the sum. I'm sorry, you get that one to see. Or using ANOVA, you can get that the same thing. See? You run ANOVA for this guy. You get the same thing. See? It's the same thing. That's a standard deviation. That's the variance of y. If you want to check for the variance of y, see, wow. Okay, I'm gonna check that one. Go to fingers and check for the data set thumb length variance. Okay, so first one. You see, 76.1552. It has a stop over here. So that's the same one. If you take the square root on that one, then you're going to get the standard deviation. That's what I'm trying to say. If you're going to call that one root mean squared, residual means the same thing. See? Standard deviation means you take the square root on 16.4. You take the square root on 16.4. You take the square root on 16.4. See? So if you take the, see, now I'm going to take the, see, SQRT on this one. 8 point. Or you can just straight go to this. Okay. Go and I can run that one too. I can run the wow and then the square root. Then you get the variance. Then square root is this much. And on the other hand, I can use this function, SD straight, for the, rather than var, I'm going to use SD of the thumb length in the fingers data. See? That would give the same answer. See? Or go to variance and then take the square root. Or go to here. See? Get the sum of squared residuals or mean squared residual and then say, find the square root. Like that. See? How many ways you can get this done? This value you already saw that one. Look at the variance. See? Sum of square. See, we already did that one. So the same way the tiny fingers data, now we're gonna see. We pretty much see. Try calculating the variance down from the large fingers data. See, fingers data. Go and do the variance of that one. See, calculate the variance of the fingers data. You can go that fingers and thumb. That's the same thing. What is the correct interpretation of the value of this one? The average square deviation in this distribution. Average square deviation. Average square deviation. Can you remember? It is average square deviation. See? Average comes from this one, square deviations. Rather than they say sum, they call the average. Because when you use the average, you don't have to mention about sum, okay? You simply say square deviation, not the sum. SSR, mean squared. Mean squared deviation, that's the same thing. As I said, see, average means mean. See, mean squared deviation. Mean squared deviation. See? MSR, MSD, mean squared residual, mean squared deviation. Average. How do you average? By dividing by not the n. Divide by n minus 1. There's a reason for that one. Okay, n minus 1 is the degrees of freedom. Why are we going to divide by n minus 1 rather than n? When you calculate the average, you normally divide by n, sample size. Here, n minus 1. See? Because you have already utilized one piece of information to estimate this guy. Here, we are supposed to have a mu. He is supposed to have a mu, not the sample mean, population mean. You say, no, I don't know the population mean. So please, I'm going to use the one piece of information to evaluate this one. One piece of information is more than enough to evaluate this one. Even though mathematically you use all the data points, abstractly, you just need only one point. That point has been already utilized in order to calculate this one. That's why you are short of 1 point. That's why you subtract 1 before you're going to average it. Average normally you divide by n only. Okay. Here in -1. That's the reason. Okay. So, the standard deviation, I already mentioned that one is a square root of that guy. I think that's the same thing. Okay. And then even that running that summary statistics, even you can check the standard deviation too. See? That's what they say. See? Here, look at calculate the standard deviation of the thumb from fingers with ST. Calculate the standard deviation with the square root and VAR. Calculate the standard deviation with the favorite steps. Okay? So many ways you can do that. And on the other hand, that calculate the standard deviation thumb from fingers. Not only that, you can see if you go to SD going to be what? SD of go to fingers, and you're going to go to thumb. See? The other one, calculate the standard deviation square root of the VAR. You go to VAR, square root SQRT of VAR of the same thing that I'm talking about here. See? Thumb length of finger. See? You close it 2 times. Okay? Calculate the standard deviation from favorite statistics. See? Another way to see. Favorite stats. See? You can say thumb and data equals, okay, fingers. Let's try this here too and see whether it should work. That's of go to fingers and put some fingers, thumb, middle finger. Calculate unexpected, calculate the standard deviation of favorite state. Step. This one. So, no. This. Calculate the standard unexpected symbol. That's the symbol. Oh, this one. No, it should be there. These fits. 8 of fingers. Okay, that's the problem. Square root. Wow, yes. That's the problem. Okay. Okay, one work SD work. See, this one work. Square root of this one work. And get rid of this one. Yeah, this one. This one tilde. Yeah, see. It's both Okay, so you can go to the thumb SD. See, that's this one. Then you can find the variance and of the that fingers, thumb length of the fingers data, and take the square root. You can come up with the same thing. Or you can find the favorite statistics. See, tilde, because it's going to go to the x-axis, like that. Or you can go to the fingers and then recall the favorite statistics. Or you can go to ANOVA. If you go to ANOVA, you make sure that you're going to run that the model. Okay, you have to definitely run the model and do that one. Okay, anyhow. See. So sum of squared. Now you have a sum of squared residual. You have variance. You have standard deviation. See. We have discussed the three ways of quantifying error around our model. All start with residual, but they aggregate those residuals in different ways for summarizing the total error. All of them are minimized at the mean, and so all are useful when the mean is the model for quantitative variables. See? What does it mean that these three measures, that means I'm talking about sum of squared SSR, S squared, and S other way. Sum of squared residual or SSR. Variance or S squared. S means simple square. Or standard deviation means S. Are minimized at the mean. These measures are smallest when the mean is the model. See? As I mentioned, can you remember I mentioned that one. SSR, not only SSR. I showed you how SSR becomes that smaller. See, SSR, S squared. See, we were talking about this one. SSR to quantify the error around the mean. See, SSR, the other one is S squared, this one is this one. You can remember this one is nothing but y minus y bar squared. This is nothing but this one get this one and divide by n minus 1. This is nothing but same thing, y minus y bar squared divided by n minus 1. Same thing. You know how we got this one, see, these three. All these three being minimum, see, are minimum when the mean is used, mean of y is, because y bar is used for the model. Mean of y bar, see, so this, see. The same way that they quantifying that mindset matters. See, now we're gonna get something that we like. See, found lost. See? If you go to this histogram, 75 housekeepers, see, mindset matters. See? You do the same thing. See, you can find the SS, Y, and SD. There are multiple correct solutions. See, so many ways you can find this one. See, there are multiple ways to compute these in R, but here is one set of possible outputs. See. Remember how you calculate SS, sum of squared residual. You have to simply run the model. That means you're going to go ahead and run LM. LM for this particular one, they were talking about, see, found, lost, see, tilde, and LM, comma, your data set, mine set matters. And then if you want to find them, then just easy that how do you find the sum of squared residual? Just run over. That's the one way, okay? There are several ways you can do. Empty dot model, see? You ran that linear model on this particular variable, pounds lost, see? Through this null model, data mindset matters, see? See the mindset matters, see? Mindset matters. And then I'm gonna run over. LN data, mindset, matters. We don't have mind, mind, yes, okay, I know what happened. One letter is missing. Mind, set matters. Set, set. So this one give you SSR, see, sum of squared residual, see, this one. Then they are looking for variance. Variance is this one, see, the next one. Then they are looking for the standard deviation, is square root of that, right? See, everything's already there. See, sum of squared residual is this one. See, then the variance is this guy. Sum of squared residual is this one. Sum of squared residual is this guy. Mean squared residual means variance. Its square root is the standard deviation. Which of the following R command would help you to figure out the SS for pounds lost? If you're going to do that one, see, var mindset matters, pound lost should be multiplied by this one. They are looking for the residual. Okay, this is what they were talking about. You have this formula. See, you have this formula. See, now they are looking for see, if you know variance, see, or I know what table you are looking for the SSR. Okay, SSR. See, you know variance var equals SSR divided by degrees of freedom, or SSR divided by n minus 1. So from this one, if you need the SSR, I'm going to bring this one and multiply by that one. See? Other way, n minus var times n minus 1. See? That's the same thing. Another way to look at it. Now, what's the code for var? Var, you can say var of that, whatever the data set, see? Mindset matters and go to pound loss times n minus 1. See? That's the same thing. See? You're going to go to mindset matters. Mindset matters. Go to pounds lost. Okay. That's the var should be multiplied by 75 minus 1. This is you can find like that way. Or go to ANOVA table and find 2. See, that's what they say. What are the ways of finding this one? So many ways. Okay. Then which of the following R command would help you to figure out the variance is in pound loss? Variance. See? Wow. See? Not this one. See? Sure, we will have to go to this one and then find that one. Okay. These ones, see, mindset matters and pound lost and the variance. No, you cannot put variance. Wow. Wow, just simply you cannot go to pound loss. You have to go to data set. Not this one, not this way. No. Make sure you all the lowercase. Okay. Which of the following R command would you help figure out standard deviation? As I mentioned, you go to favorite statistic, go to that particular data set, or SD and find it, or square root and go to the variance and find the square root, or go to SD and find it, go to favorite statistics and find it. So many ways. See, this is a new concept. That means like a way, rather than working with your y variable, you're going to standardize. Why you really need to standardize something? Because standardize means, let's say that you are taking 2 classes. In both the different classes, after the first test, you got in one class 95, the other class 85. Then you might be, by looking at just your score, you might be thinking that the class in which that you got that 95, you are doing extremely better than the other one in which that you got 85. But that's not the proper way to compare contrast. You cannot compare contrast unless that you have that common ground. You have to bring everything to a common ground. You have to compare and contrast with respect to the common line, common value. So that can be done only through something called the C-score. That's what we are doing in C-score. See, when you're going to looking into that, in which class you are really doing good, you cannot simply looking into your test score and say, hey, I'm doing better in this class, I'm not doing very well on this class, or like that. That kind of a idea you're going to get it not simply by looking at your grade. You have to make sure you go to that particular class and get the average, and get the average of the other class too. You not only average is enough. You saw that in the early beginning that we saw that average is fixed, but the variations are different. Can you remember? They vary in a different histogram. I discussed that one. You have the same mean at the center, but sometimes you have the same variation for both, same mean, same variation, but not the same sample sizes. Sometimes a different sample sizes, same mean, but the different variation. So variation of that data in that particular class should be even taken account. So eventually, instead of looking into your test score, you're going to take your test score and then you subtract your average and then divide by your standard deviation in that particular class will give you the C-score. Then you're going to get the C-score from both classes and compare and contrast and see in which class you're going to do it better. Okay? That's why we need the C-score called the common score or common ground. That's what we are trying to do. In order to do that one, what are you going to do? You're going to get your value, okay? You get your value and divide by the standard deviation. That's what they were talking about. This is what I'm going to talk about. It's called the Z-score. Means you get the Y value, you subtract your mean and divide by the standard deviation. You know how to find Y bar. You know how to find standard deviation. See? What is the number? See, this is the Z-score. This is how you're going to standardize any score. Whatever the value in any scenario, if you have a data for particular variable, if you want to standardize, go and get its this is Y bar mean its own average. S means its own standard deviation. That would tell you that how many standard deviation that point is away from that one. This is what I'm talking about. This is in the very beginning that if you have some kind of, let's say if I'm going to draw a histogram for my Y data, okay, my data, this is a histogram for my, let's say my sample, okay, for the sample, this is a sample histogram, see, you have a sample histogram, see, this is your Y value, see, this is, you say thumb length, thumb, see, on this side you have how many times it has happened, it's called the frequency denoted by F, see, you know that. And on the other hand, you can get the smooth curve scheme in that one too. Then you can locate there, say in this situation we have a symmetric one, symmetric, see, symmetric and bell-shaped, then your mean, median, highest peak, which is mode, gonna fall at the same place, see, you can remember that one. So, see, we're gonna say that I don't like to work with this value. See, let's say that if you take any value from here, let's say any value, like let's say this average is 62, you pick a value like a 65, see, then you're gonna get the gap, the difference. You really need the average, and see, and you need how much the spread in this distribution as well, which is called S. See, S, that's the spread. That's the square root of the spread, which is called standard deviation. See, you need that one. See, each and every data point, and you're gonna say, no, I'm gonna convert this into Z. See, now I'm gonna do something like this. That's the same thing. Histogram, you look the same. If you draw the histogram, same. Except for one thing, your center gonna be definitely what? 0. Because your deviations are, can you remember? The center, the error average, this is nothing but error. See, this is nothing but error. This is the error, see? That's the error. That's the residual. You know that's what we're talking about. Only difference this time, residual, we're not going to square. We're not going to take the absolute value on that one, the way that we used to do. Instead of that one, we pure residual, we go to pure residual, okay, and divide that by standard deviation to get C-score. See? Look at this setting. In a SAD, you have a sum of y minus y bar absolute. In sum of squared residual, SAD or sum of squared, I'm gonna say SAR, sum of absolute residual, this one you have this minus y bar squared. See? Then normally in the residual, if you add the residual, you have simply y minus y bar. See? Look at how different thing. Then if you want the variance, you can remember what I did. I got this guy, I got the SSR and divide by this of freedom. If you need the standard deviation, I took the square root of that guy. See? Now I need the C-score. C-score is simply residual, residual over standard deviation, which is y minus y bar over S. See? This is S. You can remember. This is S squared. This all talk about the residual. See? Look at them in different forms. This guy playing a heavy role. That's why we are doing statistics. As I mentioned in the very beginning, residual, the error, playing a key role. That means like at the end of the day, all physical phenomena in this universe are probabilistic. They have an error. When do any measurements all the time, measurements, observations, everything has an error. Error has to be minimized. That's how the big corporation, they are making tons of money by minimizing this one at the end of the day. This part is the one they heavily tackle. That's what we are doing over here. Look at how many ways we are trying to tackle the same thing. We talk about sum of absolute residual. We talk about sum of squared residual. We talk about that. It has another name. Very beautiful name for this one. Average. See, mean squared residual. See, mean squared residual. Another name. See, mean squared residual. Average squared. Average squared deviations. Other names. See? Then we talk about the standard deviation. We talk about then Z-score now. See, this is all, everything for residual, because the residual is so important. Tackle how to get this one using R. We saw that so many ways that we can get this done. We saw that. See how to get this one. Okay. Then a little bit we do this one, and I'm going to stop over here. The rest I'm going to make it to another video and then upload tomorrow. Okay. Let's see this one. They say, what is the numerator in the formula above? Numerator is nothing but the deviation or residual. Okay? Again, residual. How many residuals? See, standardized. Again, standardized. See, this is, you can call the standardized residual, another name. Residual has been standardized. That's called the Z-score. See, another name. You see, you can say the standardized residual, because the residual has been divided by the standard deviation. What do you get? Standard score, Z-score, Z-score. Sometimes we call the Z-score, Z-value. That's a standard score. Okay. Change. Okay. In this, it's a deviation. What's in the denominator? Sample standard deviation. Okay. Sample standard deviation. So here we're going to say, let's apply this formula to video game score 37,000 based on each of the two hypothetical distribution 1 and 2 above. 1 and 2 above. Where's 1 and 2 above? Okay, they were talking about these two. Okay, let me see. They were talking about there were two distributions. I see. say you have a video game called Kaggle, a friend of yours say that the high score is a 37,000 point. Is that a good score? How do you know? What else would you want to know to answer this question? Let's say that you know that the mean score across all the players of the game is 35,000. How would that help you? You would know that the score of 37,000. He got the 37,000. Average is 35,000. And then and the score 37 is above the average by really it would help. You would know that the score is 37,000. Above the average is by 2,000 points. But even though it helps you to interpret the mean, the 35, it's not enough. That's why they go ahead and include even the standard deviation, divide by the standard deviation. 37,000, and the average is 35,000. Their standard deviation is 5,000. In that case, okay, that particular game. We saw that somebody that person has a 37,000. Average is 35,000. Standard deviation for another one is one has a 500, the other one has a 1,000. Okay, that's another one. It's 1,000. Let me see. Yeah, standard deviation one is 1,000, the other one they have a different standard deviation. This one is standard deviation means the spread is far. This is smaller standard deviation which is 500. This is the same average. Two different spreads. Okay. So if that's the case, if you want to convert this to C-score, C-score is the distribution. Instead of talking about 37,000, let's see what the C-score of that my value 37,000 related to that 2. Then they say they do the same thing for the second distribution, in which that you have different standard deviation. Is 500. Is that 500? Oh, the second one. Let's say there's 1,000 points, 35. Percentage by the board distribution average of 35,000. Okay, the distribution on the top has a standard deviation 1,000 points, while the bottom one has a standard deviation 5,000. I'm sorry, not 500. 5,000. One has a 1,000, the other one has a 500. Yeah, I think this one. I am going to get back to this one. With the standard deviation 1,000 points, while the bottom one has a 5,000. This has a more spread. Okay, this is not 1,500. I'm sorry. This one should be that. This should be 1,000. The standard deviation. This is 5,000. The more spread. Okay, simply the more spread. Okay, I had in my head that is 500 and 1,000, but that's not the case. This one is 5,000. The bottom one. 5,000 is the more spread. Standard deviation, higher one standard deviation than this one. So anyhow, when you're gonna put this one and run 2 and 0.4, did you get the two distribution? This one your score. You have in this one same average but different spread. This more that your data more clustered around the this standard the mean. More data points are clustered around the mean than in this one. Here the more points are away from the mean. So now you're going to compare and contrast by looking at this one. This in both cases the numerator is the same. 37,000 minus the mean distribution which equals 2,000. The denominator for the two scores are different, though because the distribution have a different standard deviation. In distribution 1, the standard deviation 1,000, so the C-score is 2,000 divided by 1,000, which is 2. For the other distribution, standard deviation is 5,000, so it's 0.4. So the C-score can represent the number of standard deviations flow is away from whether that above or below that average. Okay, I think that I can just start from this page and then add more and then okay, and we'll do the rest on another video. Okay. And the error distribution and a little bit we can talk about it in detail. Let's see what happened. Okay, good. So the 6465 and 67, they use this different thing. But yeah, adding more distributional properties. So yeah, that to 4 through 6, 8, I'm gonna do in another video and then upload tomorrow, I think. Okay, that's the best thing because slowly and steadily I have to explain all these and then that way I don't want you to make any mistake on your homework or this test and even on the quizzes. Okay. So do you guys have any question? If not, I can wind up over here. I can stop over here and then I can just make another video and then upload into the system. Okay. Okay, no question. Then you guys have a good night and then have a nice weekend and then stay safe and be well and then see you guys on Monday. Okay. Thank you. Thank you very much. Have a good night. Thank you. Thank you. Thank you. Have a good night. Okay, April, that's your turn now.
Okay.
Okay, you see that these are so much material in this one because even for me that it takes like a long time to so much things involved this one.
Yes.
It's not easy as we think because they even look like a very easy, but so much material, programming, and then a theoretical aspect because everything has to be explained. Otherwise, you don't know what's going on.
Right. Right.
Yeah.
Yeah, I'll be going back to Monday's recording, and then that should, kind of tie in all together for tonight. So I should be good.
Make sure don't go back to the future, okay?
Okay.
Don't back to the future. It came long time ago. But anyhow, let's see that what you have to do on that. Let's get back to your home. You're still on homework 1, no?
Yes, but
Okay.
my only thing is I know how to get all the data and everything else in there, but the RStudio itself.
What's up with the RStudio then?
Okay, so I downloaded the RStudio, and then the area that says about the files, plots, packages. Well, mine is at the bottom.